Hello everyone, welcome back to this channel, and in this video we will be talking about the finite state machines as an application of sequential statements. In the previous tutorial we explored sequential statements and the different types of sequential statements within VHDL. Most programming languages are used to implement functionalities in a sequential manner, one instruction at a time. However, in hardware description languages such as VHDL, instructions are implemented concurrently. In this video, we'll explore one of the different applications of the sequential statements we talked about, which are finite state machines. Regardless of that, we will start with a review of what we've learned so far. Remember that VHDL is a language that is utilized to design digital circuits, tests the designs, and implements them in hardware. Designs are made up of design units called entities, and the architecture contains the functionality or structure of the entity. The entity is like the interface of the circuit to the outside world, while the architecture contains any other details of how the circuit behaves. Remember that VHDL is a hardware description language, and because of that, the statements written in a VHDL architecture are typically executed concurrently. We talked about concurrent statements in a few videos back, and just to sum up, there are different types of concurrent statements in VHDL, which are the concurrent signal assignment statement, the conditional signal assignment statement, the selected signal assignment statement, and the process statement. However, within a process statement, we can put statements that can be executed sequentially. Those sequential statements can be signal assignment statements, the if statement assignment, which is a sequential version of the conditional signal assignment statement, and the case statement, which is the equivalent of the concurrent statement, the selected signal assignment statement. You can take a look at our two previous videos to understand the difference between concurrent statements and sequential statements and the many types of ways you could write a concurrent or sequential statement. However, one application of sequential statements in designing circuits is the finite state machine. So what are finite state machines? Finite state machines are abstractions that allows us to solve large number of design problems. Some of these design problems can be in automation, in communication protocol design, and many other applications. As the name implies, it is a machine that can be configured in one of a finite quantity of states at a given time, where a state is a specific condition or configuration of the system. The machine, or finite state machine, can change from one state to another in response to changes in the inputs of the machine or based on the current state of the machine. Based on that change or transition from one state to another, an action will be implemented or an output will be produced. It is important to note that in a finite state machine, it can be only in one state at a time, out of the fixed number of states that the design constraints limits it to be. One common example to solidify what a finite state machine is the traffic light system. A traffic light is a machine that can either be in a red light state, a yellow light state, or a green light state. It can't be red and yellow at the same time, but rather in one state at a given time. Also, as you know, there's a sequence in which the changes occur. The traffic light cannot be green, then red, then yellow. It always has the color sequence red, yellow, green, or green, yellow, red. The sequence of states can be designed in hardware using a finite state machine. As mentioned previously, the finite state machine can change states either based on the input to the machine or based on the current state. Therefore, we have two main types of finite state machines. We have the more finite state machine and the mealy finite state machine. The more finite state machine is a finite state machine where the transition from one state to another is completely dependent on the current state. And the mealy finite state machine is dependent, the transition between the states in the mealy finite state machine is dependent on the current state and the inputs to the machine. Don't worry if you can't imagine the difference between them right now. With a couple of examples, you will get the hang of it. Okay, but how do I know which type of finite state machine is applicable to the problem I'm trying to solve with my digital circuit design? This completely depends on the system requirements. Going back to the example of a traffic light, it is obviously a more finite state machine because its transition depends on the current state, not on any external inputs. If the current state is red, then the next possible state is yellow. If it's yellow, then it's green. The next one would be green, and so forth. Okay, so why should we use sequential statements to design a finite state machine? Why not use a concurrent statement? That is because we need memory to remember the current state in the next clock cycle for us to provide that decision of the transition of states. Not only that, but when we are designing a mealy finite state machine, we don't only need to memorize the current state, or we don't only need to let the system memorize the current state, we need it to also remember the inputs for a time period so that it can implement the next transition correctly. So how can we represent states within the digital design? There are three types of encoding used within the finite state machine design. We have the binary encoding, where we encode each state in a binary number, where red can be 0, 0, yellow can be 0, 1, and the green can be 1, 0. And we have the one-hot encoding, which is a faster iteration than the binary encoding, as it converts the categorical variables into a binary format, and that essentially means we create one binary column for each new category. So if we had 4 possible states, we would have a state represented by 4 bits, where each bit represents the true or false value of whether or not the current state is that state itself. So in our example, the red light state would be represented by 001, and the yellow would be represented by 010, and the green would be represented by 100. Finally, the last type that we will talk about in this video is the gray encoding scheme. It is much faster than the binary encoding, as it only needs 1 bit change per state. So this translates into 1 bit only changing when a state changes from one to another. So applying that into our example of the traffic light system, the red light system would be represented by 0, 0. Then for the next state, which is the yellow one, we would only need to flip 1 bit, and that would be 0, 1 for the yellow. And then for the green, we would also need to flip only 1 bit rather than 2 bits as we did in the binary encoding, and therefore it would be represented by 1, 1. But which encoding can we use for our design? This is up to the designer's discretion. Each encoding has its benefits and setbacks, so it mainly comes to the optimization issue, where gray encoding may seem as the fastest one, for example, and it's better for your design. However, when we start writing code with VHDL, we don't have to worry about this. As we will see with the syntax, we don't really need to encode things using one-hot encoding or gray encoding, but rather we can create different states within VHDL's architecture to represent the finite state machine. However, when the finite state machine cycles through all the states in one path, like the traffic light system we are encountering, or like a counter, then the gray encoder would be the best choice. However, if the finite state machine is used in a system where it is really needed to run at really fast speeds, the one-hot encoding is the way to go. So it really depends on the design's constraints and requirements and the designer's, discretion. Now, looking at the syntax, how can we write, finite state machines within VHDL? First, we must create a type for the different states of the digital circuit we're trying to design. So in our case, right after the architecture and before the begin, we would need to define a type for the traffic light states and define the possible states that can be within that type. Then after creating this type, we would need to define the signals for the current state and the next state and set that equal to the type we've just defined. After that, since we're dealing with a finite state machine, we would need to be using sequential statements, and we only can use sequential statements in VHDL by using a process. So we would need to create a process within the architecture and within the process statement to represent the different transitions between each state within the finite state machine, we can use the sequential case statements as shown on the screen. Thank you for watching this video, and stay tuned for the next one where we will implement an example of the traffic light system using VHDL and simulate it through GHDL and GTK wave. And if you're interested in supporting the channel, you can do so through Patreon, where in exchange for your support, you will get the notes behind this video and others as well. And consider subscribing or joining the membership here on YouTube. Thank you again, and I'll see you in the next one.